네, 이제 다음 토픽에 대해서 이제 이야기를 해보도록 하겠습니다. 지금까지 우리는 이제 퍼포먼스에 대해서 이제 이야기를 했었고요. 특히나 이제 그 전 토픽에서는 이제 암다스 로우, 퍼포먼스의 이제 리미테이션에 대해서 이제 생각을 할 수 있는 그런 암다스 로우에 대해서 우리가 이제 조금 나누었습니다. 그 암다스 로우에서 이제 중요한 것은 우리가 어떤 아이디어를 이제 생각할 때 이 아이디어가 그 퍼포먼스의 임프루브먼트가 어느 정도까지 이제 될 수 있을 것인가. 어떤 리미테이션, 그러니까 theoretical limitation을 우리가 이제 생각해서 아이디어를 개발할 수 있다는 그런 장점이 있습니다. 어쨌든 그 improvement의 그 limitation에 대해서 이제 이야기를 하는 것이죠. 지금부터는 이제 테크놀로지, 그 컴퓨터 시스템에서 이제 테크놀로지가 이제 미치는 영향, 특히 이제 컴퓨터가 어쨌든 이제 세미컨덕터 인더스트리에 많은 영향을 받고 있기 때문에 여기서 이제 테크놀로지라고 하면은 그 세미컨덕터 인더스트리, 세미컨덕터 테크놀로지의 영향, 그 임팩트가 컴퓨터 시스템에 어떤 그런 임팩트를 가지고 있는지 이렇게 이제 이야기를 해보도록 하겠습니다. So from now on, I will talk about the impact of the technology on computer system. So until now, I explained about the performance of the computer system, and from now on, I will talk about the impact of the technology. So in this class, the technology means the CMOS technology or semiconductor technology. So this is the outline of the this class. So let's talk about the technology challenges on computer systems. So I will talk about the power consumption of the computer system or CPUs. Actually, power is the very important cost on the computer system. The computer needs the electric power, so computer consumes the electric power while the computer runs the applications. So this power is the cost of the computer system, the major cost of the computer system. So reducing power is the very important research area on the computer architecture or computer system study. So in this class, I will talk about the power source of the power consumption on the computer system. So what is the power? Power is the dissipated electric energy on the unit time. So power is the consumed electric energy during the unit time, and then energy is the power multiplied by time. So energy is the total power consumption of the computer system during within the some time duration, and then power is the power is the electric power consumption during the unit time. And then total power is the basically dynamic power plus static power, and then we frequently call static power is the leakage power. And then this is total power. Power is composed of dynamic and static power consumption, and then this equation is the dynamic power consumption. And then the next equation is the static power consumption. So in the dynamic power consumption equation, the alpha is the some activity factor of the computer's integrated circuit. So actually the CPU is the kind of integrated circuit. So and then alpha represent the activity factor. So what is the activity factor? So actually computer is the digital circuit, or the digital logic is composed of digital logic. So that means that the input and output of the digital logic is the 1 to 0 and then 0 to 1. So the electric signal change from 1 to 0 and 0 to 1. And then this is change is the activity of circuits. And then C is the capacitance of the integrated circuit. So C is proportional to the overall total area of the integrated circuit, because this circuit uh, includes some parasitic capacitance to store some electric charge. And then V is the supply voltage, and then F is the clock frequency of the circuit. So dynamic power equation is the alpha C B square and multiplied by F. And then the static power is the leakage from the supply VDD to the ground to the CMOS circuit. So actually CMOS is the voltage controlled switch, and then it's a CMOS circuit. So theoretically, one of most transistor. So that means that either PMOS transistors or nMOS transistors should be off. So off means the circuit is off from the VDD to the ground. But that is the ideal case. And then the sorry, actually the CMOS circuit is not totally insulated. So that means that it's not totally cut from the does not totally cut from the VDD to the ground, and then the leakage current flows from the VDD to the ground, even if the one of most transistor is off. So basically the static power equation is the A means the some coefficient, and then A is the area of the circuit, and then V is the supply voltage, and then I is the leakage current from the voltage VDD to the ground. So I believe you already know the power is the multiplication between V and I, and then it is multiplied by some area vector A. So it's the basic equation, and then this equation can be represented as this equation. AVE exponential minus KB, the threshold voltage VTH divided by current temperature. Then okay, so and then this is the equation of the dynamic power. So if we see this equation, then we can know some source of dynamic power dissipation in the computer chip. So what is the source of the dynamic power dissipation? Activity factor, and then C. And then C is related to the area of the circuit. And then alpha, is activity factor, is related to the activity of the circuit. But if the hardware is implemented, it is not easy to reduce this alpha and C, so activity factor and C. And then so in the dynamic power, the most important factor is supply voltage and frequency. So as you can see, the dynamic power is proportional to the V square, the square of the supply voltage. So in order to reduce the dynamic power consumption, we need to reduce the supply voltage of the circuit. And uh, as the CMOS transistors channel length is shrinked, so we can reduce this supply voltage. So as the CMOS transistor technology advanced, then the supply voltage level is also reduced. So that's the good thing of the advance of CMOS technology. And then F. F is the clock frequency. And then actually this F is tightly related to the supply voltage. So actually the Fn, basically F is proportional to the supply voltage. So you can think about some overclocking of the CPU. So if we want increase the clock frequency of some commercial CPU chip, then you need to increase the supply voltage to this CPU. Then we can increase the frequency of this CPU chip. So it is because the clock frequency of the digital circuit is basically proportional to the supply voltage. So roughly the dynamic power of the computer chip or CPU is proportional to the F3 power of 3 of F. 세제곱에 이제 비례를 하게 되고요. And then static power. Static power is not related to the clock frequency because static power is just leakage power from VDD to the ground of a CMOS circuit. So this leakage current always flow from VDD to the ground. So this static power is not related to this circuit. But this static power is also related to the number of circuits, number of CMOS logic. So this is related to the A, and then I said that leakage current flows from VDD to the ground. So this static power is proportional to the supply voltage. And then let's see this VTH and trend temperature. Actually, this equation can be represented as the AV exponential and the minus K, VTH, and V. So in this equation, if the VTH, the threshold voltage, is high, then we can reduce this leakage current. But if the VTH is low, then the leakage current will increase. So you can think the threshold voltage is some barrier of the some electron path. So you can think that if the barrier is high, then it is difficult that electron flows from VDD to the ground. Then if threshold voltage is low, that means that barrier is low. And then this leakage current is related to the T, temperature. So if the temperature is high, then the leakage current is also increases. And the low, the leakage current is leakage current decreases. So actually in the previous decades, dynamic power was more critical in the total power, but recently this static power becomes also critical power dissipation source of the CPU chip. So it is because the channel length is reduced, shrinked. So the barrier is transistor voltage also reduced. So it's very difficult to block the block the leakage current from the ground in the circuit. So recently the amount of static power is also become similar to some dynamic power. It's a very static power issue is also becomes the very critical problem of the CPU chip. And then reliability. Reliability is related to the some correct operation of the CPU circuits. So actually, every CMOS circuit device has the capacitance, and then when the switch is on the PMOS part, then the charge is filled in the capacitance of this CMOS circuit, and then if the PMOS is off and the nMOS is on, this charge is dissipated to the ground of the circuit. So actually, basically the CMOS circuit is has the capacitor devices, and then the charge is filled and charge is charged and that is charged from this capacitance. The problem is that if some energy is added into this capacitance, then the charge can be changed. Charge can change on this CMOS circuit. So if the charge changes, then the value stored into this CMOS circuit also changes. So that means that is called the B flip. And then if the B flip occurs, then the data can change in the CMOS circuit. So if the data changes, then the result of some calculation or operation can be incorrect. So that is the reliability issue. So it is also related to actually the reliability issue also increases when the channel length of the CMOS circuit is reduced. So here is a source of failure. This cosmic ray from the space or alpha particles also from the space. So this is all some source of some data failures. Also electric noises. The fluctuation of the supply voltage also cause some data errors in the CPUs. So some errors are very critical for the operation or result of this computer processor, but some errors we can ignore some errors, and so we need to determine some error. We need to determine if some detected error should be corrected or not. So it's also some important issue on the reliability issue is some important issue of some CMOS circuit or computer processor. Then also this reliability, the errors or faults has we can classify these errors and fault like intermittent temporary failures or permanent failures. So temporary failure is just a temporary failure. So this error does not last long. So it's some transient of the bit is the kind of temporary failure, and the intermittent failure it lasts longer than the temporary failure, but the failure duration is also short. So also there may be the permanent failures. So permanent failure means that device is totally break down, and then this device will not work correctly again. So in this case, we need to disable this device and then replace the device. But how can we replace the device? So we can make some spare circuit to prevent the permanent failures. So I will explain about the reliability later. And then wire delay. So actually, this wire is the is a metal. Is metal is the component of is a wire. CMOS transistor is composed of semiconductor SiO4 and then some dopant of the holes or electrons. But wire is a pure metal. So we can scale these CMOS transistors, but wire doesn't. We cannot scale. Wire delay don't scale like logic delays. That means that we cannot scale down these wires, metal wires. So what's the problem? We cannot reduce the wire delays as much as this CMOS logic delays. Actually, we cannot reduce this. Actually, the wire delay is proportional to the length of the wire and then inversely proportional to the area of this wire. So actually we cannot scale this wire delay. So actually as the CMOS transistors are scaled down, wire delay is getting more critical. So we need to control this wire delays when we implement the CPUs in the integrated circuit of the CPU. And then also we need to use some very thick metal wire for some it's a global interconnection which requires the very short delay. Also we need to use some long wires which have the long delay for some very local to connect the local CMOS logic devices. So it's a local wire. And then this wire place and routing is automatically implemented by some computer aided design tool like a CAD tool. But we need to consider how wire can be placed on these computer devices. And then design complexity is a very critical issue of the modern integrated circuit design, IC design. Actually, the Morse not due to the Morse law. Morse law is just the empirical law that observed some trend of the number of transistors on the same chip area. But what's the Morse law? The number of transistors increases actually doubles every 2 years. That means that the number of transistors on the same chip area increases exponentially, like this exponentially increases. So that means the chip design is getting more and more complex, but very much complex, much more complex every year. So it's very hard to design this entire CPU chip. So it requires many labors, many people, and then also it requires some sophisticated design. That means it will the cost of the chip manufacturing is also increases rapidly, and then it's exponentially. So So nowadays the chip manufacturing cost is very high. So only the big company like Intel or some Samsung is can survive during this in the semiconductor industry. So it's very so that is the because of some complex design issue. So and then also the problem is that when this CPU design is getting complex, it's very hard to verify this design. So verification is very important in the chip design or implementation of the CPU or computer processor. So what is the verification? So verification means that every circuit uh, needs to works as planned or works as designed. Then uh, how can we verify that this working of the computer processor? So we need to generate some vectors of the input signals, and then we need to compare the output vectors. And then if this chip design is getting, if the chip design gets more complex, then the verification effort is also very hard, it's very high. So if the chip design, the actual chip density increased exponentially, then verification, the effort for verification also will increase exponentially. So it's very hard to verify this complex CPU design. So it's a design complexity is also critical issue to implement the CPU, implement the computer processors. Then CMOS endpoint, so end of the CMOS scaling. So currently TSMC is using the 7 nanometer CMOS process, CMOS technology. So this 7 nanometer means the channel length of the CMOS transistor. So it's just what's the channel length? It's the some width of this poly on the CMOS transistor. Also, it's the some channel is the some it's the some it's a gap between this both well. So this width is getting smaller and smaller. So now it's 7 nanometer, and the Intel is using the 10 nanometer CMOS process. So, but this trend, we expect that this trend will not continue because we cannot continue shrinking this CMOS channel length, channel width. So we expect that in the near future, the CMOS scaling will end. And what will happen? That means the Moore's law is ending in the near future. So and then that means also it's very hard to increase the performance of computer processors, or it's very hard to make the better processors. So that's the problem. So think about this. If the CPU manufacturer cannot make the better processor, then customers will not purchase new CPUs or new computer system, and that's the problem. Then how can we overcome this situation? And what will come the future of the computer system? We don't actually, no one knows, and then but this end of the CMOS scaling is also some critical issue and then very challenging issue in the semiconductor industry and then computer architecture. What's the other option? Quantum computing, nanotechnology, or analog computing. But we don't know how the new technology, when and how the new technology replace this current CMOS process or CMOS technology. Okay, but yeah, we need to uh, remember that the performance is the critical design factor. Okay, so let's talk about the basic of a transistor, which compose the integrated circuit of computer processor. So if you took some semiconductor courses, then you already know about some basic operation of the most transistors. So actually this slide shows the operation of the nMOS transistor. Then what is the transistor? Actually the transistor has 3 nodes, but actually transistor has 4 nodes, like a drain source, drain, and gate, and body. So it's a fourth node, and then but in the circuit we only use the 3 nodes, like a gate, drain, source. Then what's the transistor? Transistor is the basically voltage controlled switch. What is the voltage controlled switch? So in the transistor, the electrons or hole flows between source and drain, or drain to source. So the electrons or holes flows from source to drain when the channel is generated below the gate of the transistor. Then how can generate this channel? The channel generation is a channel. It's a channel is the some 통로죠. It's a channel is a 통로 for electron or holes, and then this channel generation is determined by the voltage from gate to body. So we can control this channel, the on off of this channel with the gate voltage. So that is the some basic operation of the CMOS transistor and MOS transistor. So actually this gate voltage change the thickness of this conduction channel. It's a channel for electron or holes, and then if this gate voltage is higher than the threshold voltage VTH, then channels are formed below this gate of the MOS transistor, and the electrons are attached to the gate of the MOS transistor. Then if we set some positive voltage between the source to the drain of this MOS transistor, then through this channel, the electrons can flow from source to the drain. So that's some basic operation of the MOS transistor. So you need to so even though you cannot understand some detailed operation of the MOS transistor, but you can remember that you can just remember like this, such as a CMOS transistor is the voltage controlled switch, and then this voltage control is controlled by gate voltage, and that's it. So actually there are three regions of CMOS transistor operation, and then if you take the microelectronics course, then you learned about this three regions of operation, but this is the computer architecture course, not microelectronics course. So I will just mention that there are three regions: cutoff, the sub-threshold region, and then linear region, and then saturation region. And then actually in the digital circuit, so we only consider this cutoff or sub-threshold region and the saturation region. This is the on case, and this is the off case. So in the cutoff or sub-threshold region, then no current flows, but this is the ideal case, as I explained. Then in the modern CMOS circuit, the leakage current flows from VDD to the ground. And then in the saturation region, this current flows from the source to the drain. So the charge can be charged on the capacitance of the MOS transistor circuit, or charge can be dissipated to the ground. So some saturated region. So current flows, that means on case, and so current flows and charge can be filled or charge can be discharged. And then this is some dimension of CMOS transistor. Actually, this is the channel length or channel width. So this channel length, we represent this channel length as some technology generation of the CMOS process. So then now the for the TSMC, the channel length is the 7 nanometer, and then for the Intel, this channel length is the 10 nanometer. This is a channel width. This channel width determines some strength of the hole or electric charging. So, and then oxide thickness is actually SiO2 is a silicon dioxide, is the insulator between the gate to this body. So the TOX is the oxide thickness, and then junction depth is here, and supply voltage is the VDD, and VTH is the threshold voltage. And then actually this gate is connected to the poly of the MOS transistor, and then we connect the metal wire to the source and drain. And then okay, this is here. So actually we can, it's a very, for a computer engineer, computer science student, or was in the computer science field, the student is for the student it's not easy to understand some basic detailed operation, or some physics of the semiconductor materials. But the important factor is this channel length, and then supply voltage, and then threshold voltage. These three are the very important factor or technology factors in the semiconductor technology. And then what is the Moore's law? So Moore's law is that this size of the transistor is shrinked by years. So what is shrinked? The L is shrinked, this channel length is shrinked, And then if the channel length is reduced or shrinked, then what is also reduced? The VDD gets lower. Also, threshold voltage gets lower. And then that's very important in the performance of the CMOS transistors. So all these features scale by 1 over S, and the S is the square root of 2 every 2 years. So with this scaling factor, the number of transistors doubles every 2 years because it's the square root of 2 is the some one dimension or 1D dimension factor, 1D, and then but area is 2D, so the actually this area of the one MOS transistor becomes half every 2 years. That's the Moore's law. So this is some detailed characteristics and the scale factor of the CMOS transistor. And then you can find this scaling factor here, and then also important factor is the here. Also, as the actually, if we reduce the channel length of if we can reduce the channel length of the MOS transistor, then there are many advantages. So the capacitance is reduced, and the delay is also reduced. So 1 over S and then 1 over S. So when the channel length is shrinked, then we can make the faster transistor devices. Also, the good thing is the circuit area. Circuit area is if the scaling is done by S, then circuit area becomes the 1 over S square. Also, we can also increase the clock frequency by S because the circuit works more faster. So delay is reduced, then circuit runs faster. So there are many advantages, but disadvantage is this current, actually the leakage current of the CMOS socket. So benefit of scale. This is the benefit of scaling. So double device density, scaling dimension double device density. So we can make the smallest most transistors, most devices. Also frequency increased by 41%. That's the good thing. So actually the increasing of this performance of computer processor is resulted from the advance of the CMOS technology. So it's caused by the advance of CMOS technology. So the frequency is very important for the performance of the computer processor, and then we can easily increase the clock frequency when this MOS transistor is scaled down. Also, another good thing advantage is we can reduce the supply voltage. If we don't reduce the supply voltage, then we can increase the frequency. But if we can set the same clock frequency with the new technology, was advanced technology, then we can reduce the scaling supply voltage of the MOS transistor. So what's the advantage of reducing this supply voltage? We can reduce the power consumption. So this is the good thing. Voltage is not scaled, clock frequency can scale even faster, but dynamic power grows. So if we want reduce the dynamic power, then voltage is scaled down, but frequency is not scaled. Then dynamic power will reduce. So, but this is the disadvantage of scaling, CMOS scaling. Threshold voltage scaling scales down, so that means that the threshold voltage is reduced. That means liquid power will increase. That's the critical issue of the modern computer processor or modern integrated circuits. So this is the CMOS inverter, the logic of circuit of the CMOS inverter. And then, as I explained, you can think that this CMOS transistor is the voltage controlled switch. And then a CMOS transistor is composed of PMOS and nMOS, and then one of these MOS transistor is on and off during the operation. So in this case, the V in is the actually 0. Then the PMOS is turned on, and the nMOS is turned off. Okay, so in this case, this switch is on, then this switch is off, and then this capacitance is connected to the VDD. So if the capacitance is connected to the VDD, then this capacitance is charged. Next, the opposite case. So Vn becomes 1. So PMOS is turned off, and the nMOS is turned on. So in this case, the nMOS transistor, this capacitance is connected to the VDD via nMOS transistor. So charges are dissipated from this capacitance. So this is some basic operation of the CMOS inverter. If you remember the MOS transistor is the voltage controlled switch, then you can easily understand the operation of the CMOS circuit. The power consumption. I will explore power consumption again. So this is the dynamic power equation. Sure, we already talked about the dynamic power consumption. It's the activity factor, capacitance, supply voltage, and frequency. And then this alpha is some fraction of the clock cycle when gate switches, and then the maximum value of the alpha is the 1/2 is the clock cycle. But normally this alpha is less than the 1/2. And this is some operational factor. This alpha does not depend on the CMOS technology or CMOS scaling. About the C and VDD. C is related to the area of MOS transistor, and then if the CMOS is scaled down by S, then C can be also decreases. C can decrease. So C is decreases by 1/S, becomes 1/S. And then we already said that VDD also scales down by S, and the F can increases. So what's the result of this CMOS scaling? C is the 1/S and VDD is the 1/S square, because is the VDD square, and the F is the S. So finally, dynamic scales like 1 over S square. So it's the sum scales down of the dynamic power of one CMOS transistor. I said one CMOS transistor of the dynamic power. But as the size of a transistor is also scaled down, the number of transistors in unit area in the same area grows by S square. So by this dynamic power scaling, the dynamic power is scaled down by 1 over S square, and then area, actually the density of the transistor increased by S square, so it's the same. 1 over S square multiplied by S square. So power density stays constant. So, but we can, so this is some ideal case of some CMOS scaling or scale down of the dynamic power, but normally we need to select which factor can be scaled down. So if VDD, supply voltage, does not scale, it means the VDD is not scaled down, then power density will grow. This is because if the VDD is not scaled down by 1 over S, then it's not constant. So the problem is that actually I said that this is the ideal case, but the voltage scaling is not proportional to the some scales of scaling down of the CMOS transistor. So recently it's not easy to reduce the supply voltage. So currently we are using 1.0 or 0.9 volt for the supply voltage of the CPU chip, but nowadays it's not easy to reduce the supply voltage. So voltage scaling is not easy. If chip size grows, then total power grows. It's because the C grows. And then why we need to increase some capacitance or some size of the chip? I mean, actually the server chips or some high performance computer chip requires the various functionality and the high performance with many cores. And then power is directly related to the heat generation. And then heat is actually this heat control or is the very critical issues on the computer chip. So if the heat is not properly removed from the computer chip, then the computer chip will be broken. So heat is a very critical issue. So actually in the server system or computer processor, so it is cooling is very important. We need to cool down the temperature of this CPU processor or server processors. So heat is a very critical issue, but heat is directly related to the power consumption of the CPU processor. So that's why we need to reduce the dynamic power consumption of the CPU or computer processors. And how can we reduce the dynamic power? If you see this equation, then we can decide which factor should be reduced. And then how can we reduce this activity factor? Power gating or clock gating is some possible solutions. What is the power gating? Power gating is to cut off the connection between VDD to the ground. So actually in the power gating, is one of the most transistor is inserted between VDD to the ground, and then this most transistor is controlled by this power gating signal. So what is the benefit of the power gating? We can totally cut off some supply voltage to this CMOS circuit, so we can totally remove some power consumption by leakage or and the dynamic power. Then in reality, the power gating is not is a simple issue. So actually, the power gating should be cautiously controlled. should be cautiously controlled. 그냥 이제 파워 게이팅 같은 경우에는 서플라이 볼티지 플럭추에이션이나 이런 여러 가지 이슈가 이제 동반이 되기 때문에 굉장히 이제 실제적으로는 매우 조심해서 이제 다뤄야 되는 그런 테크닉이긴 합니다. 네. And then clock gating. The clock gating, actually the clock gating is remove some operation of the clock when this circuit is not used. But clock gating can be easily designed by the computer CAD tools, computer-aided design tool. Then this is so power gating or clock gating is some technique to some techniques to reduce the activity factor of the integrated circuits. And how can we reduce the VDD? This is the most effective approach. If we reduce the supply voltage level, then we can effectively reduce the dynamic power consumption. So it is because the VDD, so here is the square of the VDD, and so the frequency is proportional to the supply voltage. So voltage scaling is very important to reduce the dynamic power consumption. And then, so reducing VDD and then frequency reduce the power cubically. It's a power of 3. But this F, the clock frequency, is directly related to the performance of a computer processor. So this power consumption by the supply voltage and the frequency and then performance of the computer system is inversely proportional actually. So the modern computer system or modern Intel processor or AMD processor, so we can apply some dynamic voltage and frequency scaling technology to reduce the dynamic power consumption and then balance the performance of the CPU. And this dynamic clock voltage and clock scaling is called the DVFS. So it's also some important technology in the modern computer system. So scaling intelligently is very important. It's the key to preserve performance in the modern processors. So actually VDD and VTH simultaneously. The frequency does not need to scale, but clock leakage matters. Power growth. So VTH is also, this threshold voltage is critical for static power. leakage current. So we can apply the multiple threshold CMOS devices. So it's called the empty CMOS. So empty CMOS technology means that we selectively use the high leakage but best device. So that means that the BTH is very low if the speed is critical. But if the speed is not critical, then we can apply the low leakage device by setting the threshold voltage high. It's high. And then multiple voltage frequency domains is also widely used technology in the modern integrated circuit. And then power of parallelism. Okay. So let's think about the power and parallelism of the computer processor. So let's think about this baseline. So the clock period is the 1 over f. 1 over f is the clock period, and then this is the delay of the one device. It's one stage, pipeline stage. So the delay is the 16, and then we can so this baseline design can be modified to two different directions. The first direction is to divide into the more pipeline stages. So if we insert this pipelining register between this logic, then we can reduce the critical delay of this logic into half of the baseline, like 8F04 and the 8F04. And then, so in this case, we can set the same clock frequency here. So in this case, the critical delay becomes half, so we can reduce the supply voltage of this circuit here. So first approach is to divide the pipeline stage, and then the second approach is to exploit the parallelism. So copy this logic, and then put this device again. Put this device more, and then we can exploit some parallel execution with this double of CMOS devices. So in this case, we can reduce the clock frequency of this parallel operation with the half of the clock frequency of the baseline, because there are two computational logic here, and we can reduce the clock frequency to the half. So in this case, we can reduce the supply voltage by half. So that means the 1 over 4th half power consumption. So in this case, we can reduce the supply voltage by half. So it's the dynamic power is reduced by 1 over 4. So in this case, we can also reduce the supply voltage by half. So it's 1 over 4, and the frequency becomes half, so 1 over 2. But what is increased? So capacitance is increases by 2. So removed. Actually the total power consumption is 1/4. So actually total dynamic power consumption is the same for these two approaches. And how about this is the static power again. So static power is the some VDD multiplied by some leakage current, and then this is some equation of the static power. Actually, this equation comes from the some complex physical equation of the temperature, and then some CMOS transistors. But in this course, we can understand how this equation is calculated. But you need to remember that this static power is tightly related to this threshold voltage and then temperature, because Vt in this equation, the Vt is inversely proportional to the temperature. So if the temperature increases, this coefficient also increases. So that's why the leakage current increases when the high temperature at the high temperature. Also, this leakage current is related to the threshold voltage. So as threshold VTH decreases, static power increases exponentially because this. So you need to remember that this static power or static leakage current is leakage current depends on threshold voltage and temperature. And then some metrics of the power consumption and energy. Actually, power is the good metric for deciding the thermal envelope. So I said that this thermal or heat of the computer processor is related to the power consumption. So actually the peak power determines some packaging and cooling system of the computer processor. So power is the good metric for deciding the thermal envelope of the processor. And then energy. Energy is the power multiplied by operation time. So energy is the good metric in battery constrained environment like mobile devices. So even though we reduce the power consumption of the processor by half, but the performance of this processor is slowed down by 4, then energy will be 2, because energy is the power multiplied by execution time. So actually in the mobile device is very important to reduce the energy consumption. So this is another example. The test executed at the 1/2 speed. That means that it slows down to the half of the baseline operation, but power becomes the 1/4 of the baseline. That means the energy becomes half of the baseline. So that means 2 times of battery life in the mobile devices. So this is the energy is the power multiplied by time. And then also we can set some another metric, so energy multiplied by delay. So delay is related to the performance of a computer system. So energy multiplied delay, and then we simply write this metric as the ED that gives the higher weight to the performance. Then also we can use the energy multiplied by delay square, and the more weight to the performance. So this metric is used for some different kinds of devices. For example, energy can be used for the mobile devices, and energy multiplied by delay or energy multiplied by delay square can be applied for some server system, because server system the performance can be more critical. But for the mobile devices, energy is more critical. So for the mobile device, we can use the energy as some metric, and then for server system, we can use some different type of metrics. Okay, so I will stop here, and then so until now, I will explain about some basic of CMOS technology, and then scaling down of the CMOS technology and the power consumption. So actually, these are the very important metrics or the important issue in the computer system design that I explained, because the CMOS technology and the power consumption is related to the cost of the computer systems. Okay, I will stop here, and then if you have any questions, and then please post your questions on the blackboard. Okay, 수고하셨습니다. 예, 사실은 정말 저 혼자 이렇게 떠들다 보니까 너무 힘들긴 한데, 예, 잘 뭐 듣고 또 어려운 것이 있거나 뭐 질문이 있으면은 저한테 이제 질문을 메일을 보내거나 블랙보드에 올리거나 아니면은 피아자에 이제 올려주시기 바랍니다. 예, 그러면은 뭐 열심히 공부하시고요. 예, 수고 많으셨습니다.